I'm Justin Solomon. I'll be your instructor for the semester. It's a pleasure to see you all here. To get started in A37 and give us something to talk about and to give students a chance to trickle into this classroom, we'll start by watching a quick video clip of a pretty famous piece of computer graphics history here. In theory, the audio should work. Any chance you guys could scoot a little bit that way? A little quiet, huh? Sorry, it thinks the volume's at 100%, so. Just out of curiosity, how many of you guys have seen this this little animated short before? Yeah, a lot of you guys. Do you know when it was made? Oh, oops. You're killing me, guys. Yeah, in the 1980s, I think 1986. So one of the really amazing things about computer graphics technology, which of course is the topic of our discussion this semester, is that a lot of the techniques that we'll be talking about here really do date back quite a ways, at least in terms of the history of computer science. But the sort of difference is how long you're willing to wait, right? I think that probably the frames that were rendered in this animated short, if I recall, took quite some time to generate one after the next. But of course, nowadays, probably that could be done just on your laptop's graphics card, right? But really, I think this film is called Luxo Junior. It's one of the early sort of Pixar animation studio things. The director was John Lasseter, who was associated with Pixar for a long time. It's sort of one of the reflective of a lot of the things that we really love about the computer graphics world, right? They've basically taken inanimate objects and made them things that we can sympathize with. And in the meantime, simulated everything from physical interaction, motion, expression, artist directability, all of this stuff, all just in one shot. So the really amazing thing is that this technology has only improved over time, and now has moved from sort of specialized hardware and techniques that only a few people had access to. Remember that Pixar was originally a hardware company. Right? They used to make computer graphics machines, right? There's Pixar, and Silicon Graphics was another company. Silicon Graphics is no longer with us, and Pixar sort of transformed into the animation studio that we think of now. It has really become sort of a commodity and something we don't even think about, right? I mean, all of you guys pull out your phones every day, and essentially what's going on behind the display is nothing more than computer graphics technology. So the basic point of 6A37 is to basically go all the way through the computer graphics pipeline from bottom to top. Everything from how do you specify an animated scene and the motion, to rendering, physical simulation, to interaction, and a little bit on hardware. I'm a theorist, so I try to avoid that topic, but we will cover it, and with a little bit of your help and patience, we'll talk about sort of modern GPU architecture and all that good stuff. Incidentally, I apologize. I was diagnosed with a vocal cord issue, so I'm a little squeaky. If there's ever anything you can't hear, just let me know, and I'll gladly repeat, okay? Cool. So our plan for today is mostly to give you sort of an overview from 50 miles away of the computer graphics world and the different steps of the graphics pipeline. Now, when I say the graphics pipeline, this is already an extremely suspect term, right? Because of course the graphics pipeline, as it were, depends a lot on exactly what your application is, right? If you're engineering a video game, that's quite different from making something run on a cell phone, which is different from some kiosk, which is different from whatever goes on inside of an imaging device or a piece of electronics. But there's some commonalities between all of these different tools, and that's really our focus in 837, is to learn how graphics tools are built, what the algorithms are that are hiding inside of these tools, and to have you guys implement some of these things on your own. So today we'll talk a little bit about an overview of graphics, what the applications are, then we'll step sideways, talk about our administrative things. I'm sure that's all you guys really want to know on day one, like when the exams are, all that good stuff. And then we'll do a quick overview of the semester, which you'll see is basically in parallel with an overview of the computer graphics pipeline. We'll talk a bit about the assignments that you'll do in this course, and we'll conclude with a short introduction to OpenGL, which is the graphics library that we'll be using in this course, and assignment 0, which counts for 0 points, but is already posted online. If you guys don't do assignment 0, and I'll know, I can check, and you come to my office hours because you can't get assignment 1 to work on your laptop, there's going to be, very little sympathy on my part. Anyway, okay, so let's talk about computer graphics. So let's pause for a moment. So what sort of applications do you guys think of when you hear the term computer graphics? What comes to mind? Yeah. DirectX, Unity, OpenGL, so sort of maybe video game environments, 3D, interactive stuff. Absolutely. What else? Don't all speak at once. Yeah. CUDA, RTX, right? So one of the really big triumphs of computer graphics technology is that it's largely no longer used for computer graphics. So those of you who have taken a machine learning course here at MIT, I used to teach O36, will notice that much of the stuff that you do in that world sort of is accelerated by computer graphics technology, right? Like the way that we train our deep networks is basically on the GPU, which stands for graphics processing unit. And CUDA, which is this sort of programming language for communicating with that device, was sort of the first step toward that technology, and one that's a bit neglected in the history of machine learning, right? It's the reason why we can do big data, as it were. Yes? Absolutely. Well, you interact with your phone at 29.97 frames per second. Your phone is rendering two-dimensional computer graphics, right? Windows and menus and buttons and lines and all that good stuff. Vector graphics if you're using Adobe Illustrator. Anything else? How about an industry? Like what sort of, let's hear from somebody different. Russell, what's up?
The visual effects industry, some of blockbusters,
Absolutely. So visual effects is a big driver for computer graphics technology. One of the really nice things that I like as a lazy mathematician about visual effects is that CPU time doesn't matter as much, right? So there's this really frustrating thing about graphics is that your eye has a refresh rate of 29.97 frames per second. That's a phrase we hear a lot in this class. What does that mean? That means that if any computation you do in your graphics pipeline takes more than 1/30th of a second, you'll feel it. But on one side, that's like a challenge and a really exciting part of graphics is that you have this budget of time and you can spend it rendering or doing simulation, whatever. In the visual effects industry, which is where I used to work, you can spend 3 days making King Kong crash through a big bucket of water or whatever it is that he does. And that's fine, because at the end of the day, you're just going to save that simulation out. You have to render it one time, and then everybody experiences the same thing in the theater. Of course, that's beginning to change. One of the interesting questions is, let's say I want to make a movie, but I want to make it for a virtual reality environment. How much pre-computation can I do, and how much of it has to happen on the fly when somebody's using a VR device? This is a question that we have not answered yet. Other stuff. Yes? Architecture, that's a great one, right? Making a building is really expensive. And the more that we can do to simulate what it's going to look like or what the energy usage is going to be beforehand is really critical before actually making this object. Yeah? Similarly, we'll talk about finite element method and some of the sort of simulation tools in this class. And they're precisely the same ones that people use to make sure the physical system isn't going to fall apart. Yeah, 6837 is one of relatively few classes at MIT where we're pretty much in the real valued world the entire semester. Integers are less important for us. Any other ones? Yes? Biological modeling? Yeah, I have to think about that one a little bit. Certainly there's a simulation aspect there, which has a lot in common. There's also biological imaging is a really critical application of this technology. CT, MRI, and so on. All of these are basically displays hooked up to some crazy device that's like sending X-rays or God knows what through your system. Yes? Medical technology, absolutely. Now I think we've hit some of the big ones. Data visualization is a really critical application here, right? Of course, there's some intersections there between your data tends to be very high dimensional and your computer screen tends to be flat. If you like those kinds of problems, I encourage you to take 6838, which is my graduate course on geometry and covers a lot of that kind of stuff. Your colleague on your right took it last semester. Okay, so I think we've covered a lot of different graphics applications. You guys have done a much better job than past times when I've taught 837, which is awesome. But essentially, the basic point that I want you guys to take away is that computer graphics is everywhere. Also, that my slides are outdated, and Finding Nemo and Shrek are probably not the best films to show to a group of students your age. Maybe, what is this guy? This is Optimus, Bumblebee, something. He's still around. Yeah, I just watched that on a seat back the other day. But in any event, right, so computer graphics technology is everywhere, and the demands of each of these industries is a little bit different. Right, in the movies and special effects world, latency is not a big problem because they're perfectly happy to use extra computational time. In fact, when I used to work in an animation studio, there was always a lot of talk that basically there's a constant amount of computation time that goes into every frame of every movie for the last 20, 30 years. And what's the reason for that? Nothing to do with technology. Yeah.
I mean, because you can essentially wait them as patient as people are.
Exactly. Artists are the worst. If you give them a new tool, they'll push it right to its limit and try to extend it right to the end of the computation time. So for example, when I was working at Pixar, one of the big complaints they had at the time was Finding Nemo, because I'm old, was that the artist, for whatever reason, got really into modeling aquatic life. Just because it's kind of fun, you have these little swishy things in the background of a scene. And then in a single pixel of this film, right, there's this whole like ecosystem they're trying to render to decide on one color of the pixel on your screen. And so the amount of computation that was going per pixel there was just insanely large relative to what you could actually see in the movie. And it's really amazing, the amount of special effects. I think just about anything you see on TV, Netflix, whatever, is really a compilation of tons of computational techniques. I don't know how many of you guys have seen what they call visual effects reels. Has anybody? It's a really fun category on YouTube. Or if you go to the SIGGRAPH conference, you can just see these screened all day long. Essentially, oftentimes when one of these blockbuster, low entertainment value, high entertainment value, low artistic value kind of films comes out, oftentimes the movie studios will release these reels where they break down the special effects. And it's just incredible to watch. So here's one from Avengers a couple years back. I think that falls into the category of high entertainment value. We appear to be having audio problems today, but that's not really what matters here. So this, right, it's the Avengers, and the studio is Industrial Light and Magic. Oh, now it's fine. I can turn off the lights here for a second. So there's skinning, muscle simulation. These are all the assets that go into one shot. Yes. Notice the inside of his eye.
Stark Tower is about to become a beacon of self-sustaining clean energy.
Okay. I think you guys get the idea here. But essentially, one of the really amazing takeaways here is that almost nothing you see on TV is just a camera shot anymore. Even, I think we all know that the Avengers is probably digitally rendered for the most part, but even like soap operas, reality TV, and so on, all of it is digitally enhanced, some to different degrees than other. And what's really incredible is the efficiency with which people can do it, and just the degree of realism that we've managed to achieve here. Of course, one of the big points of discussion that's come up in the last couple of years has to do with fake video footage. Now this technology is so good that it's very hard to know whether you can trust video content at all, right? At this point, digital characters are often indistinguishable from human ones in film, and that creates a lot of really thorny ethical questions that are worth thinking about in the back of your head as we talk about these innocent rendering models in 837 here. But of course, it's not just movie effects that the computer graphics world cares about. There's also video games. These again are probably pretty dated video game screenshots at this point. The video game world is a very different one, right? What matters there is latency. And so what you have is a budget of computation time to do everything possible, to render the scene, to do the AI in your video game, to handle the interaction and interface with the hardware. And at any moment, if you exceed that budget of a 30th of a second, the game player notices and they are pulled out of that virtual world. Right? And so engineering in this industry, for one, is extremely stressful. The quality control is quite high and the pace of that world is very fast. But there's some really interesting engineering challenges that are quite different than what you'll encounter in your algorithms class. Right? Like there's questions you have to answer like, I can spend one more nanosecond on producing audio, but that nanosecond has to be taken out of the time that I maybe render a shadow behind some character. Right? And so there's a really fascinating interaction there, not just between different algorithms, but also between algorithms and your perception. Like, what is your eye going to notice and what are you not going to notice? And so in 837, we'll talk about color perception and some of these other kind of tricks that people use to sort of exchange computation time versus attention and how your brain processes a scene. We're really sneaky in the graphics world. Of course, related to video games are simulation tools. Before you step foot in an airplane and take it off the ground, you'll be heartened to know that we typically put you in a virtual one first, and it saves a lot of airplane money for one. And this is one of the major techniques that people use for training before they put you on the field. Industrial design is a big application of the computer graphics world. There are these two acronyms that you hear pretty often, CAD and CAM. It's also CAE. Yeah? Anybody know what CAD, CAD stands for? Yes. Computer-aided design, right? So these are tools like, like the company Autodesk comes to mind, right? Like tools like Maya and 3D Studio Max that are used to actually engineer physical objects. This is actually one of the very popular topics for research right now in the computer graphics world. One of the things that we've gotten away with for decades in graphics is making objects that are not actually physical. Really drives me nuts. Like a couple of years ago, I was in Best Buy, and they sell the TVs by like playing the blockbuster films on them, and every once in a while they'll like pause the film, and you're supposed to appreciate the pixels or whatever. And they were playing one of the Transformers, and these cars. I guess I never really thought about it. There's no conservation of mass that happens in Transformers, right? Like you have this car, and somehow it unfolds into this robot. But they pause it and there are all these intersecting polygons and you can see it because, of course when it's going by and there's, Optimus whatever exploding in your face, you don't see that like triangles are intersecting. But when you pause that frame for a second to demo your TV, you can just stand there. Anyway, I wasted a bunch of time at Best Buy really getting very upset at my colleagues in that industry. But in the CAD world, you cannot do that, right? If you have self-intersecting polygons, you can't print that anymore. Right? And so the constraints that are put on the interaction are quite different because you have to deal with manufacturability, physical realizability, and so on, right? And doing things like simulating of materials in a very accurate fashion. As somebody brought up, I think it's the first time I've ever heard here, the architecture world is a big client for computer graphics. Working with architects is like super frustrating. They want to know, like, what about like a rainy day at 2 p.m.? What is this room going to look like? And what if I replace this panel of this window with that material and so on? And it's absolutely true. The more that you can do to convince yourself that you have a realistic and nice looking environment, before you get there is really critical in being a successful architect. In fact, if you walk over to this data center, of course, is a great example of like, I would love to have been a fly on the wall when Gary was proposing that building to the MIT bureaucracy. By the way, the same technology that's used in architecture is also used, for example, to design solar panels. And like, where do I place them to maximize the amount of energy throughput that I can get into my system? It's exactly the same technology that we'll talk about for graphics for simulating light. And really, the architecture tools that we have, whoa, goodness, are quite advanced. I mean, at this point, when you want to make a building project, you can basically have an entire walkthrough of your renovation before it takes place physically. And so this has reduced the cost of building quite a bit and allowed people to be pretty creative with the way that they model these things. That's probably not amazing to you, but as to somebody that's been around computer graphics for a very long time, the fact that we can render things that are basically indistinguishable without like really examining from a real space is just amazing. Okay, this stuff maybe not so much. Okay, related to this application, of course, is virtual reality. I guess I should update virtual reality with the latest glasses that have come out. Every year there's something new. Virtual reality is one of these funny industries where like people get excited for 5 years and then it like disappears for 10 and then it comes back. And I think we're back in a time when people are very excited about this because finally we're able computationally to overcome the latency problem, right? There's nothing worse than being in a piece of VR equipment, turning your head, and then having your virtual head turn like a fraction of a second later. And finally, we have reached the point in real-time rendering where that just doesn't happen, and where the trackers and sensors that are involved in this equipment are accurate enough that really it does place you in a physical environment. Here, the latency we talked about for visual video games is really made even more challenging, right? Because you're talking about attaching a display right to your retina. In fact, the kind of funny thing is, well, I don't even think it's worth watching. I've included in the slides here a video from Microsoft from a couple years back on how they envision the virtual reality going. It's mostly, you know, smiling people and secondarily a piece of technology. Right, exactly. So it was an ad for the HoloLens before it came out. I don't think we've quite reached this point yet. This is definitely a concept video. And I'm kind of glad that we haven't, that this guy has a perfectly attractive house, but he can't see it because it's obscured by his glasses. But of course, the promise of this world is pretty amazing. Okay. As we heard back here, visualization is a really critical application here. We'll talk in 837 about how to simulate stuff. One of the sort of liberating things about the computer graphics world, we'll talk a lot about rendering and the physics of light, how it interacts with materials, bounces off of a surface, bounces in the interior, and so on. And then we'll get to the end of it and we'll say, well, why do we have to do any of that, right? At the end of the day, our job is to produce an image and it does not have to look like the real world, right? And so that suggests technologies like visualization where you can enhance people's understanding of a system that may otherwise be quite subtle, right? In fact, over the years, the movie industry has had this sort of realization that 99% of the time that goes into rendering a movie frame goes into basically simulating light bouncing around in a scene. But you know, if you watch a film from DreamWorks, Pixar, whatever, does it look like real life? No, it looks like an animated film. It's got a very particular look to it, but that look is gotten by basically physical simulation. There's a really interesting question hiding there, which is like, what if we just throw that pipeline away altogether? Can we come up with new interesting looks that are completely non-photorealistic? What are the possibilities here? And there's a really interesting kind of half creative, half technology questions to be had. And the results are really beautiful of a lot of these physical simulation tools. So here's one from SIGGRAPH from a couple years back on sort of visualizing and simulating smoke, which is one of the big sort of challenge problems in graphics world. These are definitely mathematically oriented people. By the way, I noticed that a couple students in this class are from the math department. If you want a truly terrifying piece of research to read, you should take a look at this paper here. And you can see that the visualization, the simulation here is just beautiful. Showing the sheets of smoke and how they interact with the 3D world. And we'll fast forward a bit. Of course, this is the bad one, and this is theirs, so you can kind of see the comparison. Here's one of the fun things that the computer graphics world allows us to do is to, and this really is, if you're in research in this area, one of the common ways to identify a research project basically walk around in the physical world, find a phenomenon that we're not able to simulate, make an argument that like, well, I might want to make a video that has this one very particular physical phenomenon in it. And so now I better work really hard to simulate it. And so some of the state of the art in physical simulations, it's not just in climate science or in the national laboratories, but it's actually hiding inside of the visual effects studios to really, with high accuracy, capture all of the cool things that happen in the physical world. We'll watch one more of these because they're kind of fun, and then we'll move on. By the way, every year some student proposes to implement this paper for their final project. I do not recommend that. I have never managed to do it. This is cool. I love this stuff. Isn't that neat? Just beautiful. Okay. And we will see there are certain kind of canonical computer graphics models that'll appear in this class over and over again, including on your first homework. One of them is a bunny and another is a teapot. We'll talk about those later. Of course, medical imaging is quite critical here, not just in the graphics side, but medical simulation is another big one. Right? One of the really interesting technologies now, which is sort of between graphics and HCI, human-computer interaction, is how much of surgery do you actually need to do with your hands, right? And if you have a robot that can perform it in a much more precise fashion, what visual display can you give to the doctor to make their intentions as precise as possible? And of course, there are other areas too, like things like education. There's this fun video that everybody always watches about conformal geometry. Geographic information, GPS is another big application. One of my areas of research, kind of randomly, by the way, I study geometry broadly. If anybody ever wants to talk geometry, come hang out in my office. One of the kind of funny collaborations we've had recently is in the political world, helping people with political redistricting. And it's actually really helped me learn about a whole new set of graphics tools, which are processing and displaying maps, which is a really fascinating area, right? There, the geometry is not this crazy 3D stuff we see in video games, but there's a ton of it, right? And when you interact with Google Maps and you zoom in and out from street view to world view, like trading off and moving the data between the server and the computer and displaying it in sort of a nice fluid fashion is quite a challenging problem. And of course, graphics are happening inside of any display. You guys are all experiencing computer graphics right in front of you right now, right? There's this projector screen here. There's your phone, there's the clock in the back of the classroom, the camera, what else can I spot in here? The projector is kind of the lo-fi graphics technology. But in any event, essentially, it's the point I'm trying to make to you guys is that computer graphics technology is unavoidable. And there's some really exciting and cool things to be done. So, 6837, you're all here today. What are you going to learn? Well, the basic point of 6837 is to cover computer graphics algorithms. And the basic idea here is that the computer graphics as sort of an engineering stack is like a bunch of stuff built up on top of each other layer by layer, right? It's just like anything else. If you take an operating system class or compilers, you'll learn a very similar kind of setup. But there's everything from interacting with the actual object that is producing photons and hitting the screen, to the electronic loop that has to happen between that object and a CPU, to putting actual pixel colors in a buffer, to simulating light, to going from a shape to where that shape appears on your buffer, and so on. Obviously, if you go and work at Activision, whatever, video game studio, you don't have to implement all this stuff from the bottom up every single time, right? It's often taken care of for you. And so this is why we keep using the term stack in computer graphics, right? Just like when you talk about full stack engineer in web development, anything else, right? And so our job in 837 is to build the computer graphics stack from the bottom up. We'll talk about producing pixel colors all the way to these sort of high-level questions about modeling, simulation, and so on. We will cover the basics of OpenGL. For those of you who do not know, OpenGL is one of two popular computer graphics kind of mid-stack libraries. This is different from Unity, which is like, I think, very popular now, which is sort of a higher level thing. So OpenGL is how you interface with the graphics card in your computer and sort of has the basic functionality for producing pixel colors, going from triangles to what pixels I turn on and so on. This is really a means to an end rather than something that like is a big focus in this course. This is not a class in OpenGL. OpenGL is really frustrating. They change it all the time. You know, in the process of doing your homework, we do want you to come out with some practical skill and experience, and that's where you'll get it. One thing that we do in this class that the MIT curriculum is a little bit weird about is that we will be covering C, C++ programming from the bottom up. Again, this is not the focus of our course, but rather something that if you haven't seen it before is okay and you'll get by osmosis. If you've gotten to 837, hopefully you have taken a programming class before. If you haven't, please come talk to me later. This is not a theoretical course. I'd love if it were. I would be much more qualified to teach it. But we do not expect that you know how to code in C or C++. These are still the standard programming languages in graphics industry, and for good reason, because we want to be a little bit closer to your hardware, right? And latency really matters. So that extra cost of using Python or Julia or MATLAB or whatever it is, like is just not possible. Now that's beginning to change, right? So for instance, OpenGL now has this WebGL library, which is extremely powerful and works inside of your browser with JavaScript. I've considered switching our course to that, but so far my experience is that different browsers, it doesn't quite work quite the same, and so we're not quite there yet. And plus C++, C++ programming is a good marketable skill. You should learn it anyway. So to that end, we're going to have a section, I forget what order. This week is C, C++? Yeah, so the next 2 Mondays, we will have sections that cover the basic background here. So the coming Monday will be C, C++. The Monday after that will be linear algebra, and then you're good to go. Okay, it is important to highlight things that you won't learn in this class. I don't, gotta mitigate expectations here. The 2 big libraries are OpenGL and DirectX. We're gonna learn the principles behind these and the basic ways to interface with OpenGL. All of these libraries have all kinds of crazy hacks. There's whole books about like weird ways to hack OpenGL to do crazy stuff. I encourage you to dig through those for your final project, but they're not sort of the main focus here. Right? Most of the stuff changes every like year and a half anyway. And one of the really interesting things is a lot of it doesn't matter in the sense that we're going to learn OpenGL as a means of appreciating and understanding these graphics algorithms. At the end of the day, if you use a library like Unity, a lot of these sort of low-level things will be taken care of for you. We're also not going to cover like CAD software and so on. And trust me when you say you do not want to learn artistic skills from this particular instructor. As soon as we begin talking about splines next week, you'll see what that looks like. A typical question that I get at the outset is how much math is required for 837. The prerequisite for this course is linear algebra. If you have not taken it, there are students in this class who haven't. I know, because I looked. But, and that's okay, and there are plenty of successful students in this course that don't. However, we are going to use it from day 2, right? So like starting on Tuesday, we're going to be talking about spline curves, polynomials, subdivision, all that stuff, and we're going to be writing it in linear algebra language. So at the very least, you need to know how to do matrix vector multiply. You need to know what a vector space is, what a matrix is, what linear things are, and that'll get you pretty far. Yeah. If you don't, that can be okay, but you should expect, especially in the first couple weeks, this class a little bit front-loaded, to really have to fight with it, and to come to my office hours and we'll work through it. Graphics is a math-heavy topic, and it's a bit of a different type of math than what you might be used to in computer science, right? There's a lot of computer science, there's a lot of combinatorial stuff, especially at introductory level. Graphics is all about real numbers, and so we'll talk about different coordinate systems, ordinary and partial differential equations, and how to solve them, sampling and anti-aliasing. We're gonna have the world's most gentle introduction to Fourier analysis. It was pictorial. Every year I try a slightly different set of pictures to do it schematically, and every year I fail, but we will try again. Some years it involves like bringing in a cello and demonstrating, and anyway, we'll see when we get there. But the nice thing about computer graphics is if you're still uncomfortable with these areas, you should expect to fight with them and to learn it. But the nice thing is that almost everything we'll do in this class is low dimensional, and you can just look at it, right? And render and visualize and so on. And one of the nice things, of course, is that beyond computer graphics, many of the things that we cover here are useful in other disciplines. One of the interesting things is they're not necessarily useful in computer science disciplines, but also in mechanical engineering and math, right? Things like splines, interpolation, and so on. Okay, so let's cover a little bit of the boring administrative stuff. Make sure that you guys know what the semester looks like. So, I guess this is a weird place to put this. I'm Justin, I'm your instructor. I have office hours every single Wednesday, starting, I guess, a week from yesterday from 10 to 12 in my office, which is 32D460. Incidentally, I see some people taking photos of the slides. They're already on learning modules. There are two teaching assistants, Andrew, who unfortunately cannot join us today, and Helen. She's the person who turned on the camera. So their office hours are Monday, 5 to 7 for Andrew, and Tuesday, 6 to 8. Notice your homeworks are going to be due on Wednesday. See what we did here? There's a Monday, a Tuesday, and a Wednesday. If I get an email at 1 p.m. on Wednesday and I haven't seen you in my office, you might not get a response. But that's okay. All right, so the TA office hours will be, tentatively they're in W2575. That is the former Athena cluster. I'm told there's no longer computers in there. That caught me by surprise yesterday. But it's a nice place to have office hours. And these things are still tentative, except for my office. That's not moving. Okay. In terms of stuff you should know, there's a course website. It's on Stellar, just like what many of you are probably used to. I do not use the Stellar course calendar. Everybody repeat after me. Justin does not use the Stellar course calendar. Justin does not use the Stellar course calendar. Thank you. Okay. So if you check it and there's like not an assignment due date on there, it's because I don't use it. However, we do use something else. So let me show you. Basically, there's a Google Doc that's linked from the Stellar page, which has everything you could possibly want to know about this course. Your instructor is a paranoid, color-coded, insanely organized human being. And so every day of this class is already laid out ahead of time and color-coded. Okay? So you already know all of your deadlines. This includes the project, add date, drop dead date, the drop date. The day of the, we don't call it a midterm here, it's a quiz. The final project. We'll talk more about that in a second. In order to access that, you'll need an MIT certificate, all that good stuff. Come on, PowerPoint. In addition to that, we have a Piazza page. When I get back to my office today, I'll take whatever list of people is currently registered and add them to that page. That is what you should use for communication with your course staff. That is our first line of defense. Please use that rather than emailing me directly. There's a lot of you. Okay, but in any event, all three of us, Helen, Andrew, myself, will be checking that and trying to communicate with you promptly. Our grading is as follows. There's 50% of your grade is the assignments. There's 6 assignments really. They're numbered 0 through 5. Assignment 0 is worth no credit. It's just an excuse to make sure that everything you need is set up on your computer. So plausible deniability on my part. And then assignments 1 through 5, I believe, are just 10% each of your grade. I don't believe, I know, because I made it. Then there is a final project. The instructions for your project are already on Stellar because your instructor is too organized, okay? So give them a read now. The basic way that this project goes, it is extremely open-ended. You can either do it individually or in teams of 2, and the grading will not be different between those 2. And essentially what the project asks you to do is about the equivalent of 2 homeworks worth of work, where you choose an interesting topic that you're excited about in graphics, identify either a research paper or tutorial, implement it, and write a very short kind of write-up of your results. Okay, so it's like, I think, a pretty standard project. I've tried to structure it in such a way that there's a few check-ins. So there's a project proposal. I'm warning you now, this project proposal is due the same week as your midterm. The project proposal is 1 paragraph, so I'm not terribly worried about it. But consider yourselves warned. There's a check-in, due a couple of weeks later, and then presentations and report. There's a quiz. This is code word for midterm. Yeah, that'll be a couple days before the drop deadline, and we will be sure to get your grades on that before it's too late to drop this course. Of course, you should not drop this course. I love every single one of you, but I know that many students want that piece of data. And then finally, there are 10 nano quizzes. I think this MIT phenomenon. I'd never encountered nano quizzes before I came here. But I think roughly every other class that's marked on that calendar, there's a nano quiz, which will be just the first couple minutes of class. You can either do it digitally on Piazza, like answer the questions there, or I'll give you a sheet of paper and we'll grade, whatever you prefer. Are there any questions about grading, course policy, all that good stuff? Cool. All right, and I already mentioned the course calendar. Ooh, a transition. Okay. Yeah, in terms of prerequisites, oh, yes.
So what does the nano quiz like test specifically? Is it just like stuff covered in lecture or things?
That's a good question. Yeah, so it is everything up to including 5 minutes before that nano quiz you're responsible for it. And so it's basically the lecture content until then. They're designed to be easy. Yeah. This class is filmed, and I'll put links to YouTube videos when I remember to post them. There's high probability that the camera will break or the audio quality will be bad or so on. 2/3 of the internet likes to remind me of that in my email. You are responsible for the contents of this course regardless of whether there is video online. Okay, nods? Cool. So the video is just meant as a backup and a resource to you guys. It is not meant as a thing that you primarily can depend on. I've gotten a few emails from students asking, can I skip every lecture, watch the videos, and get credit for this course? The official answer is no. Will I be taking attendance in these lectures? No. So you do you. You want to take the risk? Go for it. But going to our TA and saying that I can't take any of the nano quizzes because I have a conflict every week, is their answer, whether they know it or not, is no, I'm sorry, I can't administer it at another time. If you have an emergency, of course, with S cubes, go ahead, we'll come up with alternative arrangements. Okay. Right, so the prerequisites, all the assignments are C, but we're going to cover that. The official prerequisites for the course are just programming, calculus, and linear algebra. Okay, and we'll announce the location for the review sessions on Mondays, ASAP. That's my bad, I forgot before class. In terms of your assignments, you will turn in both a piece of code and an executable, like a compiled piece of code. Everybody repeat after me. I will turn in code and an executable. My code will run on the Athena machines. Cool. So here's the challenge. Computer graphics technology runs slightly different on every piece of hardware. This has been a frustration ever since I've taught graphics in the 90s. Everybody's laptop is different. Every computer is different. OpenGL has different versions and so on. We have tried to design the experiments, the assignments so that you can compile and run them on Windows, Mac, or Linux. However, at the end of the day, we will be grading on Athena machines, and that is the way we're going to check. So when you submit your homework, before you submit it, you should put it on an Athena machine, compile it, run it, make sure it looks the way you expect, and then submit. Okay, this is the only way that we can grade in a fair way. Okay, there are physical Athena machines on campus. I'm told that the ones in W20 are no longer there, but we will we'll follow up with some places you can actually find clusters. I know this stuff is boring. Finally, there's 3 late days. These are 24-hour late days. It's not like this weird generalized, like every lecture late day. Okay, you are for every day that you don't turn in your homework beyond those late days, you lose 25% additively. This is not like compound interest. So after 4 days, you get no credit for your assignment, and you cannot use it for any piece of your final project. I'm serious, people. Of course, again, if you're having an emergency or health issue or you're overwhelmed and so on, I totally understand. MIT is a very difficult place to be. What I will ask is that you go to the S cubed office first, get clearance from them, and then we'll work together to come up with a suitable plan to make up stuff. But the policy in this course is that if you do not do that, this is the policy for late assignments. Okay. Finally, in terms of collaboration, you can chat, but your code has to be your own. Your final projects are on pairs of 2. You're welcome to post any questions you want on Piazza, and I encourage you guys to answer said questions so that I don't have to. It's really great. So just in your README when you submit your projects, be sure to let us know who you worked with. It's nothing negative. We want you guys to work together, but we also do want to make sure you're all writing code. Okay. And my one warning is that the assignments are a lot of work. Okay? There are 5 of them. They're hard to compile and just to get running. Again, graphics hardware is annoying, and that's life. I hate it. But that's life. So as soon as you receive the assignment, download it and at least compile the starter code just to make sure it runs on your machine. Because if it's midnight the night before it's due and you can't even get like a window to appear on your computer, you're going to be in tough cookies. Okay? Cool. All right, so finally that concludes the administrative stuff. There's like lots of fun assignments in this course. We're gonna have a quick warm-up where you load and display a mesh. We're Our next piece of our course will be on curves and surfaces, then hierarchical modeling and skinning, like, I have a skeleton that I'm animating. How do I actually move the skin with the skeleton? Physically based animation, so like we'll do simulation of a piece of cloth and a little bit of collision. Ray tracing, which is a particular rendering technique, and then a real-time graphics, like interfacing with your graphics card. The main point of failure is this last one, in terms of like hardware and crazy stuff going wrong. Okay. And then the project instructions I already talked about. There's no textbook for this course, but there are many textbooks out there. If you want pointers, this list is a little out of date, but I'm happy to send some. Okay. So now let's talk about the semester and all the different fun topics we're going to cover in 6837. So the basic question we're going to answer, when you open up your video game, I play lots of tractor, themed video games. How do you go about making this picture? Like, what ingredients go into this thing? And there's many different pieces, right? So the first thing that we'll start with is before we even communicate with our hardware in terms of how to draw this picture, we have to communicate what's in the image, right? And so we'll first talk about modeling, which includes geometry. This is my personal favorite part of this course. Materials, lighting, and so on. Everything that you need to specify a 3D scene. From there, we'll also talk about sort of another virtual piece of our scene, which is animation. How do we make things move? We'll talk about different types of animation. There's artist control animation, right? Where like I'm like giving different poses or maybe doing inverse kinematics where I kind of move characters around. We'll also talk about physically based animation. Physically based animation is kind of a funny, politically correct term, right? It's physically based because we're not going to be too concerned about getting the details of a physical system right. The goal is to make sure you perceive that a physical system is proceeding the way you expect it to. It's a slightly different problem to solve. And then we'll talk about rendering. Like, how do you actually draw this thing? So how do you go from the description of a scene and motion into actual pixel colors, including lighting, shadows, textures, and so on? And so roughly this is just the way our semester is going to proceed. And then sort of sitting underneath this is a grab bag of topics involving graphics hardware, and, so certain standard specifications and so on. So that's our basic overview of our semester. We'll talk about modeling, animation, ray tracing, which is one type of rendering algorithm, and then the sort of hardware-based rendering algorithm after that. These are all ridiculously fun topics. One kind of funny thing about the way this course is organized is that every lecture is almost on a different topic. That means you miss a lecture, you should watch it for sure. You should also come to the next one. Some of them will build on each other, but actually many will not, because this is the way graphics works. It's just like this giant hodgepodge of different techniques that you need to make a graphic system. So we'll start out by talking about modeling. This includes curves and surfaces, subdivision, and so on. These are sort of, how do you go about specifying your animated character? Anybody know this guy's name? His name is Jerry. In any event, it was one of the early animated short films. And essentially, it was also, oftentimes you'll see in front of animated movies, they'll have a little short ahead of it. Right, like, I don't know, what are some of the recent ones? There's like Luna with the guy that was sweeping up the stars on the moon. And there was some god-awful, ridiculously long one in front of that Pixar movie about the Day of the Dead, which I think involved the characters from Frozen. But in any event, oftentimes those are sort of serve two purposes. One is to entertain you. The other is to test out a new piece of technology. And so Jerry, from the film Jerry's Game, is a good example, where they were testing out the use of something called subdivision surfaces, which is something we'll cover in this class. The idea of subdivision surface is that essentially, when we talk about geometry, when we're rendering, it's going to be composed of millions and millions of little facets, like squares, triangles, and so on. Having an artist sit there and place every vertex of every triangle is obviously impractical. And so often we give them sort of a high-level set of controls to move the characters around. So in the subdivision surface world, maybe what they do is they specify something we call a control polygon. That's like these yellow curves here. And then behind the scenes, the computer fills in some smooth surface that obeys something that looks roughly like that. So we'll talk about what that technology looks like and how to implement it, and that's what you do in your first homework. After that, we'll talk about transformations. This is going to be tons of linear algebra, right? So after you have modeled Jerry, your next task is to put Jerry in a scene, right? And so that means that you need to rotate him, translate him, and stick him in a spot. That stuff is basically linear algebra. It's stuff that you know. There's a bit of an added twist here, which is that scaling a 3D shape, that's a linear transformation, right? I can take the vertices, multiply it by a matrix that multiplies everything by 2. Is translation linear? Remember that a linear operator means that, like, you know, linear of x plus y is the same as linear of x plus linear of y, so on. Turns out that translation is actually not linear. It's simple, but it's not linear. And similarly, projecting shapes onto the camera plane, like doing perspective projection, is not linear. So what we're going to show, we're going to talk about something called homogeneous coordinates, where if we want to talk about 3D, we'll have vectors with 4 numbers in them, and we'll see that that'll sort of resolve that little missing piece. If you like projective geometry, if you're a math student, there's some cool stuff hiding there. We'll talk about perspective and some of the crazy like fisheye lenses and so on. After we've set up our scene, of course, we need our characters to move. We'll talk about a couple different types of keyframing. One famous type is called, a couple different types of animation, one of which is called keyframing. Exactly what it sounds like, right? Just the artist places a few frames. Again, remember that your final video is 29.97 frames per second. More than that if it's a soap opera, by the way. That's a different story. But obviously you don't want your artist to sit there and in between every single frame. And so we need to talk about technology for how to interpolate between sort of sparsely placed constraints on animated characters. We'll also talk about skinning, which is a technique that goes from an animated skeleton to an animated motion of some crazy video game character. Skinning is a really critical piece of the graphics pipeline because, again, we want really complex stuff to emerge from a pretty simple set of controls. Right? And so skinning, you'll need to deal with the elasticity of the skin. For people that are not your instructor, there's things like muscle bulge and so on, all of which are really critical to get right. And then finally, we'll talk about physically based animation, so things like particle systems and physics with quotations marks around it for doing things like fire, smoke, and cloth. These are by far the most popular topics in 837 for your final projects. Okay, so finally, we have done everything we need to specify an animated thing except actually draw the damn thing. And so that's what we'll spend most of the rest of this course. We'll talk about 2 major types of rendering algorithms. The first is called ray casting or ray tracing. In my mind, these are basically synonyms. Some graphics people, there's a slight difference between the 2. We'll talk about that so that you can use it at your favorite pub trivia. Ray tracing is an algorithm that is easy to implement, can capture tons of physical interactions and really beautiful scenes in just a few lines of code, but it's hella slow is the technical term. So you guys will implement all kinds of different tools for shadows and reflections and all this neat stuff. The only problem is that it'll take like maybe 30 seconds to generate a frame. That'll be enough for us to cover lots of topics like texturing and shading, anti-aliasing. Right? Your pixels are like some finite grid, but of course inside of a pixel there's like lots of stuff, like 10 different sea anemones that you have to summarize with one color. And there's some really neat theory hiding behind how to do that in a way that's visually imperceptible. And we'll talk about fun extensions of ray tracing. So here's a very famous 3D scene. I'm going to keep asking this even though nobody knows the answers. Does anybody know what this 3D scene is called? This is called the Cornell box. Yeah? Somebody told me it's named after somebody by the last name of Cornell, but then somebody else told me it was Cornell University, and I never Googled it, so I'll let one of you guys do that. In any event, this scene is composed of 2 things, a reflective sphere and a refractive sphere, so like a piece of glass. Is this a physically plausible scene? I mean, initially it kind of looks like 3D stuff. That's what I mean. Like this rendering, what goes wrong? You guys spot anything wrong? Maybe somebody else. Yes. Yeah, there's a shadow underneath a transparent piece of glass. Anything else?
The shadows are really hard.
Shadows are really hard. Absolutely. Yeah. Oh, you just okay. Cool. Yep. So of course, what we'd like to do is go from a scene that looks like this to a scene that looks like that. Right? And so notice, for example, the piece of glass is focusing the light underneath the shape. There's interreflection between the floor and the ceiling, and that the shadows are soft. We'll see is that each one of these is just a couple extra lines of code in your ray tracer, which incurs a stupid amount of additional computation time. Yeah? We'll also talk about shadows, which are easy to do in the ray tracing pipeline and quite difficult to do in the real-time graphics pipeline. And this is going to be our means of transitioning from really slow, beautiful graphics to really fast, high throughput graphics. I think shadows are the best example where the algorithms for handling them are completely different. So in ray tracing, you're just simulating light bouncing around a scene, so shadows kind of happen organically. In the other technique we'll talk about in your graphics hardware called rasterization, it's closer to like how you would paint a scene, right? Like you're given a canvas and you're given color and your job is to just like paint one object after the next, right? So in that case, shadows are kind of annoying, right? Because you know, if you just look at a pixel and you say, is this pixel in a shadow or not, it's a sort of second order computation you have to do to figure that out. Right? And so that'll transition us to what people traditionally think of as this sort of rendering pipeline. Aesthetically, there's sort of just a flip of a for loop that happens between ray tracing and rasterization. So in ray tracing, for every pixel, you kind of trace a line out and you figure out the first object it runs into and you render it. In rasterization, you iterate over every object you're going to render it and draw them one at a time. Right? And so, yeah, okay, these are, you know, if you write it this way, it seems pretty simple. But the ways that we're going to accelerate these techniques are quite different. Right? So in the rasterization pipeline, we're going to talk about like clipping, like throwing away objects that you can't see in a scene, figuring out what objects are actually visible, which ones are on top. All these sorts of things are quite challenging to do. So then finally, we know how to draw stuff. So then we'll have a fun grab bag of other topics. We'll talk about color and perception. You know, discuss the usual, like, is that dress, what is it, blue and black or yellow and gold? We'll talk a bit about display technology, virtual reality, augmented reality, and other topics. If you guys have things that you're really excited about in graphics that are a little more kind of topical and niche, let me know toward the beginning of the course and we'll see what we can do to incorporate a little bit of it. Okay. For the last couple of minutes we have remaining, I thought I'd tell you a little bit about the assignments we have, and then we'll talk a tiny bit about OpenGL, but I'm mainly going to defer that because for assignment 0, you'll only need a tiny, tiny bit, and so I'll leave the slides there for you to page through, but then we're going to kind of return to the heavy-duty OpenGL at the end of the semester. We talk about real-time graphics, okay? So again, you got a bunch of different assignments. Your first one's on curves and surfaces, so you'll implement a technique that takes a few control points for some curves and fills out a nice, smooth object. And then you'll take that curve and you'll sweep it around a second curve to make a 3D surface. It's a pretty standard technique in computer-aided design. In assignment 2, we'll do hierarchical modeling and skinning. Right? So first thing you'll do is, it would be really annoying if I wanted to pose my 3D character by writing the position of like every finger and your nose and your ears in terms of like, you know, coordinate system relative to like the corner of the room or something. Right? So the more typical thing to do is to write like the position of your hand relative to your arm, and your arm relative to your upper arm relative to your chest, and so on. Right? And so there's this little piece of kind of graphics algorithm you have to implement to move up and down that stack of coordinate systems in an efficient fashion. That's going to be not sort of conceptually that hard, but kind of annoying to code because it's recursive and people get that wrong a lot. And then to just make it worse, skinning sort of happens in global coordinates, but all of your skeleton bones are in these local things. And so you're going to have to write some code that kind of reconciles those two pieces. Your third assignment, you're going to simulate a piece of cloth. So you're going to implement some very simple differential equation simulators, nothing complicated, just something called forward Euler and I always want to say RG3, but that's a football player. What am I thinking? RK4 integration. Which is just a few lines of code. Essentially, this is going to be the kind of code where your code is short, but if you get one character wrong, your piece of cloth is going to explode. Your next assignment is to implement some rendering tools. So we'll draw lots of spheres in this course because they're easy to intersect with lines. We'll also have triangles and cubes and all that good stuff. And then finally, just to frustrate the students, we have one assignment in real-time graphics where you're going to render a scene and then render it with shadows. And shadows are really, really tricky because when you render a scene, of course, you have your camera and you're drawing all of your objects. The real-time graphics way of rendering shadows, typically, not always, but typically, is you render the scene twice. You actually render it once from the perspective of the light bulb, and that tells you what location of the scene actually received light. And then you render it a second time from the camera, and then you kind of look up from one into the other to figure out how to color your pixels. And so there's some really irritating calculations you have to get just right, or else like, you know, you'll move your light this way and the shadow will like move that way, You know, it's really crazy stuff. I love debugging this. You guys come to my office with all kinds of really ugly stuff. Okay. So for the remainder of our class today, we'll give you a tiny introduction to OpenGL, just enough to kind of understand what's going on in assignment 0. Again, you're all going to go home and download assignment 0 and try it like right now, yeah? I see you back there. I don't like that head shake. I'm watching you now. Okay, right, so OpenGL is an API, right? It's a programming interface that allows you to send commands to your graphics card without, talking about electrons. And it's a sort of a basic tool for rendering 2D, 3D graphics, right? It'll handle stuff like, is this pixel inside of a triangle or not, and so on. One of the kind of cool things is that OpenGL is, it's kind of a funny piece of graphics technology where typically technology over the years gets more complicated and more convoluted. OpenGL has removed many features over the years. The reason for that is that it used to be in computer graphics, there was a very sort of prescribed set of steps that everybody followed, like first I have my triangles, and then I figure out what pixels are inside of what triangles, and then I shade them, and so on. Nowadays, what people want is control. And so what OpenGL provides you is a simple way to interface with your graphics card, and then it's up to you what your pipeline looks like. Yeah? And so it actually has a little specialized programming language built into OpenGL. It's kind of funny, like it'll be in your C++ code, this other language called GLSL, which you'll use to communicate shader stuff. So in assignment 0, you've got a very exciting assignment. You're going to load up all the triangles in this teapot. He's secretly composed of many, many triangles. I believe 1,300 if I recall. And render it in OpenGL. So just using simple colors and a very simple shading model. You are encouraged to, but not required to turn it in on Wednesday. If you do, your TAs will provide you feedback, probably not detailed feedback, just like, yep, it's a go, you turned it in correctly, we were able to run it. It's just a good way to sanity check so that you're good for the remaining assignments. And you'll get to learn some simple 3D stuff in OpenGL. So for just a little bit of basics, 3D scenes are big piles of triangles. You might not have known that, but now you do. So if you zoom in really closely to your 3D characters, they tend to look like what I'm showing you here. If you take 6838, we'll talk about all kinds of weird things you can do to triangulated surfaces. In this class, they're largely just a long list of triangles and vertex positions. And essentially what OpenGL is a giant sledgehammer for taking a list of triangles, sending it to your graphics card, and drawing them on the screen. At least that's what it was maybe 10, 20 years ago. Okay, so of course, at every vertex, we need to store a certain amount of information. We need to store where it is in 3D. By the way, do we really need to store where it is in 3D? Does that actually matter for rendering? No, we just need to know where it is on the screen. Yeah. We'll see that in OpenGL, it's actually better to put the 3D information on your graphics card and leave it there, so when you move your camera, you don't have to like DMA your whole bunny across to the computer, to the graphics card a second time. You probably want to store the color, maybe per vertex, maybe not. We'll come back to that. You'll have to store a normal for every vertex. Do you guys know what a normal vector is? If this is a surface, this is a normal vector. It points 90 degrees away from the surface. Maybe some information about transparency, texture, so on, but you're not going to need that for assignment 0. If you're wondering why do we actually need surface normals, you're going to implement the world's simplest shading model in homework 0, which is to say that the light that bounces off of a point on a surface is proportional to the dot product between the vector to the light and the surface normal. Let's do a sanity check here. Let's say that the light is this way and the surface normal is 90 degrees away from it. What color will my pixel be? Black. You see why? Because dot products between orthogonal things are 0. Does that make sense? What does that mean? Well, that means that the light is coming at the surface and it's just moving right past, right? It's not actually hitting it. Yeah? Similarly, when do I get the most light? When I'm pointing right at the light. Yeah? Well, at least from a sanity check standpoint, that makes sense. This shading model is something called Lambertian shading. It's really good for rendering terracotta pots. That's about it. But it's also the one that you'll implement just because it's like one line of code. Incidentally, you guys laugh. Remember, in this assignment, you'll have a teapot. That was sort of the very first one of the sort of spline surfaces that was ever modeled in Utah. Another famous surface in the computer graphics world is the 3D bunny. It's called the Stanford Bunny. You can go to the Computer Museum in San Jose and actually pay homage to the Stanford Bunny. I have many times. The Stanford Bunny is actually a terracotta lawn ornament. And the reason why is that not only is Lambertian shading easy to render, it's also easy to invert, right? So that was one of the very first 3D scanned objects because the lighting is so predictable that you could kind of go back from like a photograph of this object to the 3D shape. Yeah. Okay. So in any event, how do you draw? Well, for now, you tell OpenGL to draw. In this course, of course, we're going to fill in the details here. But you have to give it some information. You have to give it vertices, and also like where your camera is. Essentially a projection matrix, which is going to take you from 3D vertices to the image plane. Okay? So that sort of high-level pseudocode is you kind of set up all the different callbacks you're going to need. Like, remember, the graphics code is not like algorithms class, right? Like, once 30 times a second, it's going to ask your keyboard, like, did you have anything to say in that last 30th of a second, right? That's how this interaction works. You're also going to load and compile vertex and fragment shaders. We'll come back to that in a moment. And then for every frame, you have to manage your UI, update your camera, and draw. Okay? So the basic graphics pipeline looks something like this. What comes in is something called a vertex buffer. It's like all the geometry in your scene. Then we're going to encounter this term for the first time in this course right now, which is something called a shader. Something really frustrating. Do shaders necessarily have anything to do with shading? Not anymore. They used to. So there's two types of shaders. Well, there are many types, but there are two types that we'll cover in this course. A vertex shader and a fragment shader. In principle, this is a little piece of code where behind the scenes, your graphics card puts a giant for loop over every vertex of your geometry, so every vertex of every triangle, and you get to execute that code per vertex. So as input, maybe you're given all the information on the vertex, then you can output more information per vertex. So for instance, maybe I have the positions of the 3D bunny, and I want the position of where those would be on the computer screen, so that would be like a per vertex thing. Then behind the scenes, there's assembly and rasterization, where OpenGL says, okay, I now know where the 3 vertices of my triangle are on the computer screen. What pixels are going to light up by virtue of the positions of those 3 vertices, right? Like over here. And then for each one of those pixels, a piece of code gets called a fragment shader. That is your chance to do things like shading, right? Because that has to happen on a per pixel level. And then finally, the output of the fragment shader goes into something called the frame buffer, which is nothing more than an array of pixel colors. Okay? Trivia fact. How many times let's say that I have a 100 by 100 image. How many times do fragment shaders get called? That's right. There's a trick question. The obvious answer would be 100 squared, right? 1 per pixel. But that's actually not true. So if I render 10 triangles that overlap, every time I render a new triangle, the fragment shader will call a piece of code to shade that triangle. And then it'll ask you, okay, but which one's on top? And we'll go back. There are some clever reasons for why that's the case. Okay. So in a tiny bit more detail here, your vertex shader sort of inputs per vertex information. You can do all kinds of stuff like transform the vertices and then outputs more per vertex information like coordinates in screen space, maybe positions in the texture map, and so on. Vertex shaders are pretty simple to read. This is a new programming language for you guys that is not quite C++. It's called GLSL. Stands for OpenGL Shading Language. You're going to write that mostly in assignment 5 and a little bit in assignment 0. So GLSL has some information like positions and so on. Uniform means that this is a piece of information that every single vertex of my mesh is going to need. So for instance, the camera matrix is one matrix for your whole scene, right? And every single vertex is going to need it. Then there are other ones that they call varying, and that's going to be like the per vertex information. And then you sort of say like, okay, well, this is the output per vertex. And then here, so for example, I'm taking the position in 3D, multiplying it by the model view projection matrix, MVP. Isn't that cute? And then what comes out is the position on the screen, and that's what gets output. Okay. So for now, you guys can just pattern match. That's what you'll do in assignment 0. And then we're going to talk in detail in assignment 5. And you're going to write lots of shaders for like shadows and rendering and all that good stuff. Then what happens behind the scenes inside of your graphics card, there's a dedicated piece of hardware to figuring out what pixels are inside of a triangle. Because that happens so often in your computer. So that's something called a fixed function rasterizer. And then you call the fragment shader, which we already talked about. And basically the code looks the same, right? There's some uniform information like the position of the light. There's some varying information like the normal to the triangle, and then you can output your color based on that. Your assignment 0 is very tricky, so you got commented out the one line of code you have to write. Okay. Right, so that's basically all of assignment 0. Of course, there are many things that are missing: shadows, shininess, textures, all that good stuff. I encourage you to play with your assignment and implement as many of those as you can just for fun. Incidentally, many of the assignments have extra credit on them. Go for it, go crazy. However, you must retain the basic functionality of the assignment or we can't grade it. Cool? One way to get around that, if you're like super excited about extra credit, there's always one of you, is to save a version of your assignment that is just the assignment, and then submit a second one with all the other cool stuff you did. I would say that's the best insurance policy. Okay, and the one sort of remaining note here is that linear algebra is going to be everywhere starting from day 1. So just get excited. Everything we already saw dot product today in class. We already saw matrix vector multiply and moving the camera around. This is no mistake. This is the principal tool that we'll need in computer graphics class. So with that, just about concludes my discussion for the day. Are there any questions that you guys have about 837 as we get started here? Yes?
Is Jerry the guy who paints Woody's foot in Toy Story 2?
That's a great question. Any other questions about... I have no idea. Could be. All right, well, with that, it's been a pleasure. I'll see you guys on Tuesday.